So today I'd like to talk about something we call Dtrace for developers. For those of you who are in the FreeBSD community, you may have seen that Robert Watson and myself have been developing coursework around operating systems, teaching operating systems using Dtrace. Robert has developed a graduate course for graduate students at the University of Cambridge. I have worked with Benedict Rauschling to develop an undergraduate course, which we have taught occasionally during breaks in Darmstadt at his university. And then I spend quite a bit of time explaining Dtrace to developers, people like you, and how they can use it. And we'll go into that presently. Oh, that does work. So how many people here have used Dtrace? Well, at least some of you. Usually I have no hands. So what is Dtrace? It's a dynamic tracing framework for software. The goal is to have a low impact on overall system's performance, because if your tracing system requires 100% of your system, then you're not doing much productive work. And then there's this last line that I always like to point out. The goal is that it doesn't incur costs when not in use. So I'll talk about that quite a bit, or I'll mention that as we go through. So, as developers, we really care, if I'm trying to explain a tool to someone, what does it give you? So Dtrace can show you a lot of things about a running system. And one of the ways in which I like to think about Dtrace is it's runtime debugging and runtime collection. So people are used to using a debugger, but that means the program has usually been stopped. Watch points are one thing, but they're not really very much. So Dtrace can show you quite a bit about both user space applications and the kernel, including things like when is a function being called, what arguments were passed to that function, and things like the frequency of various system and function calls within a piece of software, and a whole lot more, which we'll talk about. So here's a quick example, and I'll explain a bit about what's going on later. But on a running system, you can use Dtrace to say something like, show me all of the system calls. So if you can read this from the back, I don't know, you'll see that when we start up Dtrace, it says that there's 2,148 probes. So in Dtrace parlance, in the way Dtrace works, every single point in the system at which you can ask a question about what is going on is called a probe, or we would call it a trace point, but usually it's a probe. So we can do things like tell the system to look at every single system call that's running as the system's executing. So how does Dtrace work? So when the kernel or an application or any other piece of software on the system is built, there's a tool that takes the object files from your compiled C or C++, and looks at the object file and finds where all of the function entry and exit points are, and then it creates a new section in the object file, and it adds probes to the system, so that when you activate Dtrace and you say something like, tell me about this particular function, the kernel can actually figure out where that's supposed to be, and then they're activated using the Dtrace program. Now, when the program is activated, when Dtrace is activated, for instance, if you're looking at a function entry point, it replaces the entry point with a jump instruction to somewhere else in the code, and it's a jump to basically the probe code. So does anybody know another piece of software that works that way? What was that? SystemTab's
similar, not quite.
SystemTab is similar. I'm looking for something else.
No. GCC had profiling options.
The answer I'm looking for is it's basically a rootkit. Right? That is how rootkits work. So Dtrace is a rootkit for your operating system. It's a really nice rootkit, which is why we only allow it to operate when you're root. But it works exactly the way rootkits do. It changes the instruction stream such that you're going off to some other piece of code. But because it changes those assembly instructions at runtime as opposed to at compile time, that's why the overhead is 0. because we know where to go find the function, but we don't actually change the instruction stream until you say, please tell me about this particular function in the system. So this is my canonical complex example, and I'm going to go through this in the following slides. But for instance, it turns out many people write really poor user-level code. I know that kernel-level programmers like to say this all the time. So one of the things you might look for in a misbehaving piece of code is sort of looking for when someone calls write with a very small number. Because people will do this thing of like, I just want to write these 8 bytes. And you're like, yeah, but you really are writing much more than that. So this line on line 1 is, well, the first line is the actual command that we're typing. And then as Dtrace executes, it starts printing out a bunch of data. So this line here says, for the write system call on its entry, when the second argument to write is not 0, tell us what the size was. Right? So now people who do 0-byte writes are terrible people, but let's not worry about them yet. So this is something that you could do to a running system to find out, you know, if there's a program that's doing lots of small writes. Let's walk through this. So let's talk about some of the things we need to understand or define to know how to work with Dtrace. Because Dtrace is a fairly large, complex system, and it's got its own scripting language, which we'll look at briefly. It's able to look into a lot of parts of the system, so it's got its own vocabulary, or glossary in this case. So when we talk about a probe, that is the entire way of specifying what to trace. So in the previous example, I wanted to look at the entry point to the write system call. That is the probe point that we're talking about. There are tens of thousands of probes in FreeBSD and in macOS, and the OpenBSD folks have been working on doing a port of Dtrace as well. But you know, when you compile the kernel and a bunch of user-space programs, you get tens of thousands, sometimes hundreds of thousands of probe points. So a probe is a way of saying, I want to look at that thing. Probes are broken down into a few abstractions. So we have something we call providers. And a provider is a way of Dtrace talking about various things that it can look at. So you saw in the previous slide that I wanted to look at system calls. And so syscall at the left is a provider. So there are a variety of providers we'll talk about. System calls and FBTs, function boundary trace points, are the two most common that programmers use. And that's sort of the top level abstraction. Everything comes under some form of provider. Providers can have within them modules, which could be, so for instance, in the kernel, if you have a KLD, a kernel loadable module, then it will show up at, the name of the module will show up in the module column. So that's the next narrower thing. Within modules, you have functions. We all know what functions are: read, write, open, close, all of that stuff. So these three things are the way of shrinking down or narrowing what we're going to talk about, narrowing down the probe point, how we're going to pick a probe point. Then we have two other things which were used in the previous example, and we'll go through these a little bit more as well. We have something called a predicate. So how many people have programmed in awk? Wow, young people who program in awk. This is great. The people who wrote D loved awk, and so if you know what predicates are in awk, then they'll make a lot of sense. But a predicate is a way of saying, even though I want you to look at all the write system calls, I only want you to execute the probe when certain conditions exist. So that was that arg2 not equal to 0. That's a predicate. And you need that because if you were to, so for instance, if you were right now on a busy FreeBSD box to say, turn on all system calls, like trace all system calls, the system would not crash. And Dtrace is extremely safe for a bunch of reasons, which I will probably not go into, but you generally cannot crash Dtrace. And if you make the system go very slow, Dtrace kicks you out. So if you try to Dtrace too much, and there's a watchdog within Dtrace, and it's like, wow, I'm running really slowly. Who's making me do this? It's like, oh, you? And it kills you. It aborts you. It doesn't abort the system. Because it turns out, panicking your kernel makes a very bad debugging experience. So predicates are a way of filtering down the amount of output. Because if you were to say, for instance, show me all writes on a busy system, you'd get a ton of output. And so predicates are a way of saying, well, only if there are errors, or only if the size is this, or only if they go a particular direction. Lastly, we have actions. So again, in that previous slide, and actually I'll go back to this one because this is slightly longer. So here's your probe point, provider. There's no module because you don't need one. Function, entry point, predicate, which says arg2 not equal to 0. But lastly, we have this little bit of C-like code. So D has an entire scripting language that looks like C. Now, for those of us who've written C for many years, we might ask, why would anyone make another language look like C? Because it's a terrible, horrible language that's very painful to work with. But when kernel developers write a system, they always write it looking like C. So, printf, this should look just like a printf you would see in C. And this action between the braces is what's going to actually be executed when the probe point fires. Without that, you would just get a bunch of output that says the probe point fired, but you wouldn't get any data. So actions are where a lot of the work gets done in a D script. So probe, that's the whole thing. Provider, module, function, that's how we figure out what we're going to look at. Predicate is a way of filtering, and then we have these actions that fire once we're doing something. They collect data or they print data out. I said that there were many providers. This is a short list. And this is actually this was the default list when Dtrace was originally built for Solaris, which is where Dtrace comes from. You've already seen the syscall provider. There's a profile provider which says fire every, you can say something like fire every 100 milliseconds or fire every second or something like that. You can look at process operations, you can look at the scheduler, general I/O, a bunch of networking providers, IP, UDP, TCP. There's now an SCTP provider, BFS for some file system operations. But FBT is the largest collection of probe points on any system. And the function boundary trace point, which means entry and exit of every function in every compiled C or C++ file built on the system, these are generated every time the compiler runs. So when you do a build world on FreeBSD, we build all of these for all of the programs that we do in build world. And we build it for the kernel when you do build kernel. So when you rebuild your kernel without any, you don't have to set any options. By default, the kernel build process not only takes the source code and turns it into object code, but also runs a tool called CTF convert that builds these big sets of trace points. So this will change every time someone changes the kernel, right? This is not, system calls are fairly static. Thankfully, people don't add or remove system calls very often. But every time someone changes a kernel function, the function boundary trace points will change, which actually is great because before Dtrace, almost all logging and tracing systems for debugging required you to write a bunch of macros, right? And that meant that the programmer had to stick the macro in the right place. And as those of us who have debugged large pieces of software know, you have never put the macro in the right place for the bug, right? So you're like, oh, I need another macro to rebuild this system. It takes a week for the bug to show up. It's terrible. So this takes the work away from the programmer. It just means when you run the compiler, you will also get all the trace points every time you compile your system. So this is a sort of the default set of providers. There are more now. I talked about how to dissect this. So we talked about syscall write entry, so the provider is syscall. There's no module, double colon. For those of you who've ever looked at IPv6, double colon is the wildcard. Function, and then we can say entry. Different provider, this is the function boundary trace point. In FreeBSD, ether input is the central point at which all Ethernet packets go through to get into the network stack. So if I want to look at every inbound Ethernet packet, irrespective of interface, like I could have a 30 interface machine, they'll all eventually go through this. So my provider here is the function boundary trace point provider. My module is the kernel. My function is ether input, and I want to know about the entry. And you can do entry and return. You can look at the return point of any function when it returns. Dtrace requirements, well, I could probably remove this now because we're way past FreeBSD 10. We're about to release 12. But on FreeBSD 10 or later, it was just completely default. You need to be root. And then there is a Dtrace manual page. One of the things I like to point out when I talk about this is you really cannot depend on Google to find you answers to Dtrace because Oracle bought Sun and then they messed everything up. So like the Oracle documentation on Solaris or Illumos or whatever, their stuff is appalling. So look at the manual page on FreeBSD, and then there's some other references we can talk about. And we've been actually adding newer manual pages to FreeBSD that cover things like the providers. So just ignore the Oracle. My advice is ignore the Oracle documentation. If Google takes you to Oracle, go look for something else. Which actually should be true generally, just like their software and also Dtrace. Okay, so in that previous slide, I pointed out that during that particular compile of my kernel, I had 50,000 probes. Right, so how do I find a probe that I want? So you can do things like you can say, show me all the probes in the syscall provider. You can actually do it by module, so you can find the probes that are in your KLD. You can do various things with -p means use the provider. You can say look at the module with -m, but Dtrace-L will list. If you say Dtrace-L like on your Mac, I've discovered for some reason it executes forever. I haven't figured out what's wrong, but I'm going to go talk to the Apple OS developers and find out why. The other cool thing, so Dtrace doesn't just know about functions, it knows about arguments, right? Because it's got your object code. So you can say LV, for instance, and it'll say, well, not only, here's the probe point, but here are the arguments, right? And we know, for those of us who've worked with Unix a long time, reads have a file descriptor, which is an integer, a pointer to a buffer, and then the size, hopefully the correct size, of the buffer. So you can do -lv and find out more about, you don't have to go read the source code to find out what the arguments are to a function. You can ask Dtrace, which is probably a lot easier than using cscope and global to look through 10 million lines of FreeBSD. So this is how you find the probe arguments. So I mentioned that D is a powerful subset of C. It includes features specific to Dtrace, such as aggregations, which I'll mention later because they're extremely useful. Anything beyond certain simple debugging, usually you wind up writing a script. So there are sort of two things to look at in Dtrace when you're thinking about how to write something to pull out some data from the system. There's something called Dtrace One-Liners. Like that syscall thing was a one-liner. What that means is it all fits on a line. Now, it might fit on a 256-character line, like it's not an 80-character line. But if you Google for Dtrace One-Liners, that's actually kind of useful because we've been maintaining some pretty good wiki pages on those. But anything complicated, like if you want to do some analysis of the system, which you can do with D, usually requires a few pages of code. And so that's written in D. I mean, those printfs are D as well, but you can create D scripts. Oh, and by the way, if you ever decide to write a language, like a computer language, don't name it with a single character. Because it turns out that search engines are terrible. And it also turns out there are two D languages. There's the D language for this, and there's a compiled D language that people thought they would use as a child of C, which there's some people who use it, but it's very hard to search for a single letter. So please, 3 or 4 letters might be more helpful. So we talked about Dtrace One-Liners. Here's a few examples. This is first line is saying, show me all open calls. Oh, and you can see we can use wildcards because there's more than one type of open on the operating system. Anything that looks like open with an entry, tell us the program that tried to open it, and then tell us what the path was. What did they try to open? Next one is just being able to count system calls, to use abusing the system, syscall by syscall, and I'll talk a bit about this syntax with these @ characters, which is an aggregation, in a moment. So here's this example of counting system calls. This is a relatively idle system, which you can tell because clock get time is one of the most frequently called things. This is an aggregation. And so what aggregations do is instead of just spitting out output every time a trace point is passed, Aggregations collect up information about a trace point, and then when the script exits, when you hit Control C, it gives you, you see Control C here, it gives you this output. So I want to talk about aggregations because they're one of the most powerful things in D, especially for analysis. If you just want to see what arguments are going by really quickly, that's simpler. But aggregations give you the ability to do a whole bunch of interesting analysis of a running system. So that's this at probe func syntax. Now you can make an aggregation without anything here, and that would be sort of like a simple count. But the idea is that it aggregates data during a run for later output. One of the nice things on FreeBSD is we have something called, or on BSDs generally, by the way, is SIGINFO. In fact, if you want to get a bunch of Unix people really annoyed, ask them when SIGINFO is going to run on Linux, because it's like the dividing line. It's like the VI and Emacs of running a system. It's like, oh, why don't they have SIGINFO? So on FreeBSD, and I guess this will work on Open when they get there, if you hit Control T, it dumps the aggregation. It's like, oh, you want to know some output? Here's how much I've aggregated so far, which is kind of cool from the command line. The reason I mention this is that it's often surprising to first-time Dtrace users. They'll look at a one-liner, they'll do an aggregation, they'll run it, and they'll be like, why is there no output? And that's because D is collecting all this data. So if you want output, you have to Control C the script, or Control T and get the partial output. So aggregations. So here's an example of a complicated aggregation. And what this is doing, we've got the comment at the top, but we're summarizing the requested write sizes by the program name. So this little ASCII graph, and for those of us who also love Ministat, we're like, this is fine. And then there are people who do UX and UI stuff, and they're like, that's hideous, but for us, this is fine. This is all done automatically. Right? You don't have to write any code to make this little graph come out. This is just what an aggregation does. So we say syscall write entry, we use the at, and then we say, okay, we want this indexed by exec name. So you can see that in this particular case, because the output goes off far off the screen, this is find. So my usual demo when I'm giving the longer class is I'll run find on my little virtual machine, because that causes a bunch of I/O to happen. And so that'll give Dtrace something to look at, because if there's nothing going on, Dtrace doesn't show you. A run, it doesn't show you very much. So what this is showing is, on the left, this is a bucketized by powers of 2 size of the writes. They were quantized, and then the count. Right? So the largest number of writes are somewhere between 16 and 64. They're in this 32. Right? And then there's 59 here, so they're very small, and then we get to 0. But the nice thing about aggregations is it's automatic. It's part of the system. You don't have to write Perl code or shell script or whatever or Python to take a bunch of output and reduce it. It's part of D, which is great. And it makes basically first level analysis of software a lot easier. So we can look at, there's a bunch of other things we can look at. So we talk about probe points. We can also look at the stack. So for instance, you're trying to find out, how this thing that's breaking keeps getting called. You can actually find the stack. So for instance, this is a simple call to stack. We read upwards. This is when we enter the kernel. System call, system read, kern read v, do file read, which means we're going to try and do actual read data from a file. And then I happen to be a kernel programmer, so I know that this is vnode stuff. And we're trying to get some memory because we want to read into that memory. But okay, so that's mildly interesting. But if you were to use, and there's an example in the full slides which are online, if you use stacks with an aggregation, you can then find out basically what is being called most frequently. It's a very easy way to do a first level of performance analysis. There's also something called the Dtrace Toolkit, which we maintain online, written by Brendan Gregg. It's a huge number of scripts that were originally written for Solaris when he was a performance analysis person there. Now he's working at Netflix doing different performance analysis. So it's all written in D, a little bit of Perl, which I think we finally converted to shell script. Originally specific to Solaris, exists as a FreeBSD port and package, and we continue to update that with new scripts. So the Dtrace toolkit is a really good place to look for examples if you don't, if you're looking for something to figure out a problem. So here's an example script. This is something called hot kernel, and this is what's going to tell us on a busy system, except this is not a busy system, what's doing the most work. So if you've got some sort of storage system, or you've got a networking system, or you've got a very busy box, and you run hot kernel, it'll do this it just is sampling. This is really doing aggregations. When you hit Control C, you'll get all this output. This is an idle system because it's mostly putting itself into C1. So I mentioned predicates, talking about filtering probes to get relevant data. Really useful for common conditions like, sometimes if you're looking at system calls, you want to say, only show me a system call if error no is not 0. But if the system call caused an error, then tell me something. But if the system call executed normally and returned without changing error no, don't bother. This is arg0, but error no is available to D scripts. So we can also do things, we can track the kernel, but we can also track any user space process. So we can use the PID variable in D to say, show me only things that happen to come from PID, whatever it is, 234 in this case, or whatever your PID is. So since I do a lot of kernel work, I spend a lot of time just telling Dtrace to probe the kernel. But you can also run a program under Dtrace. So you can attach to a PID once it's running, but you can also just run a command under it. If the command always fails or the command always has a problem, you can just run it under Dtrace. So I mentioned this thing about the fact that Dtrace will not let you destroy the kernel. Right? There's a watchdog. It makes sure that it's making progress. If it's not making progress, it kicks out your Dtrace command. But you could slow the system down, right? You can push the system such that your programs are not making as much progress as they were. And you can do that by doing things like telling it to look at if you were to trace every function boundary trace point on a busy system, suddenly Dtrace would be using up a whole core because it'd be a lot of data that it's copying out of the kernel. Which doesn't mean you can't do it. It just means don't expect to be able to trace everything in a running system all the time and have the system perform the same way it did when Dtrace wasn't running. So if you register a probe on just a module, you can go too far. The other thing to realize, and I should keep an eye on this, is that the more you look at, and it's not linear, the more you look at, the slower the more overhead Dtrace will introduce. Now, Dtrace can actually run with very small percentage if you're just doing certain probes. But for instance, on a research project I work on, we're trying to use Dtrace and leave it on all the time. It's a security project. We're trying to basically look for intrusion, use Dtrace for intrusion detection to the system, which means we're looking at everything always. Now, it's a research project that's well-funded, so we have very big boxes. But you wouldn't want to always do that. So things to remember when you're using Dtrace, and especially for people who decide to use it like to build a monitoring system, you can do that, right? I mean, this is what Sun did this, Fishworks did this, which was a sub part of Sun that used Dtrace tremendously. They built a ZFS-based storage appliance that all of their monitoring was just Dtrace. They just used Dtrace and then they put it into a nicer user interface. But as you add probe points, you have costs, overhead costs. When you add that action code, that C-like code, that's an interpreted language, which is compiled down to bytecode when you start it, but it's still executing bytecode. So the action code requires time to run, and it will have an impact on system performance. So it's free when off, which is great because earlier logging systems weren't, because they all had if statements in them, right? If the logging is on, then do this. If it's not, then do that. That kind of probing has a measurable overhead. In D and in Dtrace, you have no impact when you've compiled the code, but once you turn on the tracing, you'll see an impact. But it won't destroy the system, and it's not 100% impact. But it's measurable. Let's not do the. Here we go. So where's the little flag? I'm not up to 30 minutes yet. Okay, good. So a lot of what I often talk about is tracing the kernel, but Dtrace can be applied in user space really effectively. So, we can look into a process with PID and the target variables, which work like function boundary trace points. So we can run programs under -C, and we can attach to a running daemon, like if you've got daemon processes with -P to find the probes in user space. Let's see if I can do this. So here's my quick demo. Hello, escape. Where's my, that's not what I want. That one. Let's cheat. Dtrace.
Can you change the font size?
You want it bigger? I mean, I'm the one wearing the glasses. Let's just make sure I can drag the window up a little bit. Okay. Is that what I want? I'm cheating like my own slides. Okay. How do I do this? I'm really going to cheat. Oh well. All right, give me a second. All right, let me just pop back into this. So, yeah, that should work. All right, I'm not going to mess with that demo. I should have practiced this before. Anyway, so presentation. So we can actually look into, and here's output from a previous run, a running process. So you see, in this case, we have PID 3722, which is because when I executed ls, it happened to be that process. But Dtrace will list out all of the functions in ls because when build world executed, CTF convert tore ls apart and put in these sections. So, it turns out ls happens to have a usage function, but also it shows us things like libc, right? So we can see what's going on in libc. In this case, so in the kernel case, we saw like FPT or syscall for the provider. In the user space case, the provider is the PID, right? Now, that means that each time you would actually get a different PID, so you use a variable called target, which I'll show you, which you can look at later. In this case, the module turns out to either be the program, ls, the executable, or one of the libraries, libc or any other library that's linked into the program. And the function's a function, just like usual. And then you can either get things like entry or return, but one other thing you get in user space is a hex offset. So you can't effectively list all of the probe points in a user space executable, because if you do it without any filtering, it will not only show you the entry and the return, it'll show you the hex offset of every instruction in every function. And at that point, Dtrace is like, you've asked me for too much data, stop. So you kind of have to be a bit more aggressive at filtering. But it's quite cool, because unlike in the kernel where we can't easily look at hex offsets with the current providers, in LS, I can say not only show me usage, right, the entry into usage, but I can say, oh, in this function in LS, I know there's an error that seems to occur between these 10 lines, so trace only those 10 lines. So for those of us who've used debuggers to do that, it's actually a very powerful feature, and you can list them out. So you can create a probe point on any instruction. So, listing a function without entry or exit. And so these functions are just hexadecimal offsets. So here's an example I can steal from my own slides. Let's do that. I'm always a fan of stealing from my own slides. So if I have to make that much bigger. Let's hope it works. Tick, PID, target, colon, under malloc. Colon, tick dash CLS. There you go. So LS's output still comes out. This is not part of the Dtrace stuff. But when I executed this, I got, okay, so good, we can see this. So here's Dtrace minus list. N says list from a probe, and I list the probe as PID $target. So that means no matter what PID LS is assigned when the system executes it, it'll fill this in automatically. I don't have to guess that the next PID is 12955. Like D handles that, because it would be terrible to have to guess. And then I say, oh, well, show me malloc, right? Which I happen to know is under malloc when it's compiled. And then Dtrace gives me this output is like, oh, okay, well, PID whatever, we don't care, that's going to change every time. Here's your libc module, and then there's an entry, a return, and then you see all of these numbers, and you see they go into hex. It does annoy me that the output doesn't say 0x before the hex numbers, but this is the hex address of every instruction in malloc. So you can say something like, oh, only probe malloc at instruction 2D, right? So you're like, oh, I happen to guess that something goes wrong in that part of malloc. Tell me if it ever returns there. Or in C, you can return from any point in a function, right? You can return from anywhere. So you can set it on a bunch of return points. Very useful for debugging user space programs. Hooray for giving myself examples I can use. So something to understand about return values, how many people have read the C ABI? Excellent, because it's a terrible read and it will make you very sleepy. So an entry points make perfect sense to most people. They're like, oh, well, I know that there were 4 arguments, and arg0 is the 0th argument, and arg1 is arg. But in the C ABI, function returns have a very specific way of being returned. So in the Dtrace system, we follow the C ABI, obviously. And when you ask for arg0, well, what does arg0 for a return mean, right? So arg0 happens to mean, in the ABI, the return address. Where did we return from? So you saw that thing where we were looking at malloc. We can find out, did I return from the end of the function, which is probably an okay return, or did I return because there was an error in the middle? And then arg1 is the return value. So for a return probe in kernel space or user space, these are always the same because of the C ABI. So arg0 is the address we returned from within the function, and then arg1 is the value that was returned. So we can do this thing of tracing malloc. I am not going to type this whole thing in. I mean, I've got some scripts for it. But again, we're looking at PID $target malloc. We want to look at the return, and then we see, so-and-so allocated this size, because we look at arg1, from offset that. So arg1, arg0. And then that'll allow us to see what the return values are. Again, we can use things like predicates. So if we happen to know using hex dump that we know that this address is this line in the code, or by using a debugger, we can say, well, do we ever return from this address? We use a predicate that says only fire the probe when we happen to return from this place in the function. Nice wallpaper. Let's not do the lab. Is that the pizza?
Not yet.
Okay. So also in user space, we have something called user space dynamic tracing. These are trace points that you can tell the Dtrace tools to add to your user space code. We have the same thing in the kernel called SDT, which is, there's no user there. So I mentioned this thing that before Dtrace, you had to hand add probes, right? Everyone would have a debug macro. Everyone's seen debug macros, right? If def debug, blah, 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 blah. Dtrace has support for a really nice version of that, because instead of it being a bunch of if statements, which mess up your code, it uses the same tricks as like the function boundary trace point. You put in a macro that's a special macro understood by Dtrace, and it will then at runtime do the assembly instruction replacement for you, instead of actually dumping a bunch of macro code into your system. These are called USDTs. They're slightly different. They're different from the bid provider. And so you in your user space programs, or if you're a kernel programmer in the kernel, can add your own trace points. Cheap, and they all work with Dtrace, which means that you can use aggregations with them, and all of your D scripts will be able to talk to these things in your system. That's called the USDT provider, similar to the one in the kernel. So this is an example from some online code from Alan Hargraves, who wrote this a million years ago. This should look really familiar. It's a loop of hello world, because we're all going to write hello world from now until the end of time. The reason it's in a loop is this makes the example easier to use, right? If you didn't have the program do something a few times, you wouldn't see any output. It would run once, and that would be it. So it's a loop version of hello world. We add a single macro, which is predefined for us, called Dtrace probe1, because we want to know about the loop variable, and then when we run Dtrace, we'll get the loops out. We then make this horrific file called a probe description file. For most simple probes that you'd want to add to a user space program, just use a template. Just like grab this out of examples and use it. The folks at Sun did a great job of making it so that you could specify things like, is this function, is this thing usable on Intel and Spark? Because it turns out those are their two architectures. So you have things like, is this an evolving provider? Is this a private provider? All these different attributes. You can ignore all of that. Just steal this code and put this bit in. And that's how everybody writes software anyway. We all go to Stacktrace and then we download it and we execute it and we're done. It's the modern world. We had one different line to our build process. So, hello.c, and then we use Dtrace. Actually, Dtrace is used for all things Dtrace. It's used for turning on the probes. It's used for getting the data out. It's also used for compiling the probes into a new object. So you see there's an object file. We take this probes.d, and then we finish compiling and we link it all together. You cannot call the D file, this file here, cannot be called by the same name as the object. So, as a programmer, you're kind of like, well, I've got, network.o. Why don't I have network.c and network.d? But turns out they collide, so you have to have a different name. I usually just call it probes.d. And then the resulting executable has all the probe points in it. let's ignore stability. I want to get through this a bit. Dependency. Let's not do the lab. And I'll talk briefly before someone waves a red flag at me about doing the same thing for kernel code. There's enough people I know here who've had to deal with the kernel that this probably matters. So the goal of SDTs is the same as the goal of the probe points I showed you for user space. We don't want to have code littered with printf. In fact, I have a slide somewhere, it might be here, that says death to printf. Printf is a terrible debugging tool. Or, take a wild guess how many different debug macros are in the FreeBSD kernel. There's one for every developer who's ever worked on the kernel. There's currently like 50, so there are not thousands. But, everyone's like, oh, I need a debug macro. So their driver has their own debug macro. Oh, I need one for this. And there's like another one. You're like, could you stop? So anyway, they're great for converting logging code. So I did this for TCP Debug. So many, many years ago, when I was young and did not have hair, because generally I started shaving my head young, but there was an option added to not FreeBSD, not OpenBSD, not NetBSD, but BSD, like the BSD, called Tcp Debug, and it was used to debug the early TCP stack. I think by Loeffler, who wrote the stack. It's really a rarely enabled kernel option. It's been there for, not a million years, 500,000 years. And it gives stuff that you'd be interested in if you were trying to debug a TCP stack, TCP connection. Tells you which direction the data was going, what the state of the socket was, what the sequence space looked like, which is important for TCP, and then a bunch of the variables in the TCP stack. The code itself was fairly compact, 127 lines, 14 calls to printf. So anyone who's ever had to implement printf on a system knows that printf is expensive and awful. So every one of those is expensive. And then it had this statically defined ring buffer of 100 entries. Why? Because it was written for a VAX. So for those of you who are old enough to remember a VAX, it was a very large computer with a very small memory. It was a 32-bit machine. You could have put 4 gig in it, but you could never have bought the boards. So it had this tiny little ring, and it had a static log format, right? So now you think about, it's 30 years later, you have Dtrace. It'd be really nice to do this in a flexible way, where you could say, I have a bunch of probe points, but maybe I only want to look at certain arguments, right? And I want to leave this on a lot more. So I went and did this conversion. So when I was done, we got 4 new trace points. They're in FreeBSD 11, definitely. I think I MFC'd them to 10 because someone nagged me. So we get 4 new probe points: debug input, output, user, drop. They reflect what was in the TCP debug output. So you can actually, and I've done this, you can replicate the exact output of TCP debug option with Dtrace for, 4% increase in your CPU utilization. And there's some researchers using this to build some tools. So you get access to TCP and socket structures, and you have a flexible log format. So how do I do it? Well, I use the macros that already exist. So we can declare a provider, which is a new, you saw syscall, you saw all that stuff, so debug's the new provider. You can define the provider, you declare the probes, you define the probes. So it's like, I have a probe, and the define is like, these are the arguments. You define translators, which I'll cover very quickly. But these macros, the way you do this in user space and the way you do this in the kernel are different. This is the stuff for the kernel. The user stuff is what I showed in the previous slides. So, we got 4 lines of declaration. This was, where was this? Debug. So this is in TCP input, which is, anyone ever read TCP input? TCP input is how TCP packets are processed in any of the BSD operating systems. It is a very long function, which does a lot of stuff. But the original TCP debug code, had to do all these checks, and then it would always call into the trace function if this was enabled, right? So this is expensive. All I had to do was add one more probe macro outside the ifdef. It's always on. I mean, it's always compiled in, not always on. Always compiled in, and you always get access to it. And I'll explain the arguments in this case. So instead of having the data printf out in a particular format that Sam or someone decided on in Berkeley 30 years ago, what we actually are giving people access to is the TCP protocol block, which is sort of all of the things about your connection, a pointer to the structure, a pointer to the header, and then access to the mbuff, the actual data, right? So you can write D scripts that can do things like look inside the structure and decide to only look at one part of the structure instead of getting this static output. And then, since I've only got 2 minutes, this is going to be hilarious because translators usually take me an hour to explain to the class. But translators exist specifically to take something like a TCP info structure, TCP PCB, which is the thing all about everything in TCP, and turn it into a convenient representation for. It's supposed to be human readable, but what I really mean is programmer readable because programmers are not human. And then you get this really nice bit of scripting. So these scripts are all in FreeBSD now. You can find them in user lib dtrace. This is the probe point debug input. This is we make sure debug is turned on because you can turn debug on and off on the socket, and then we just gather all this data and print it out any way we want. This happens to print it out in the same format that was created 30 years ago. You can do anything you want. Let's not walk through the whole thing. So, how much work was that? Because programmers are lazy. I'm very lazy. It was basically a 200-line code change, 160 lines of example code so that other people could use it. It was a few hours of poking around, and I tested it over a day or two, and now we have always-on TCP debugging. You can actually leave this on and watch a socket, and the socket will not perform terribly. Like, if you're trying to do, please don't do high-performance trading, or financial stuff while that's on. But, if you had turned on TCP debug on a long-distance TCP connection, the connection would drop because you would have timeouts. With Dtrace, you don't. All right, so then I will leave this on the lab exercise that we're not going to do because I probably have 30 seconds left. So are there brief questions? And then people can ask me the long, complicated ones over pizza.
Complicated.
Excellent. I'm looking forward to pizza. Yes.
Are the user space probes available only for C and C++, or can it work with other languages like Go or Rust?
So it is possible to do any compiled language, but I do not know. I do not know of. I think there are probes for Go now. I would like them for Rust because I like Rust better than Go. And I am pretty sure they exist for Swift because the Apple folks are huge fans of Dtrace. I actually found out that Dtrace runs on this, which is terrifying. It's only not in the release version, but I'm like, you put Dtrace on a watch, which seems like a bad idea. But it'll work for any compiled language. Have always been Java. You've always been able to use it for Java because Sun, right? Because Sun created Dtrace. But I don't know if there's a Rust setup. There is a Go setup. I don't know how good it is. So I haven't written much in Go.
Thanks.
Okay, Sasha's taking me off.
All right.
Thank you.